So my name is Karpov, and I work as a software developer at JetBrains, where most of the time I'm working on C# support for ReSharper and Rider. About a year ago, as part of my job, I implemented support for C#8 feature called Async Streams. But as times go by, lots of important things happened. Most notably, C#8 was finally released and people started adopting new language features. So I thought this event is a great opportunity to look back, see what's changed, complete some unfinished tasks, and, share some experiences. And let's start. And the first part is exploring diversity with effects. So all applications in some or another way interact with data, and the kind of data and application requirements usually define the most appropriate way of interaction. And whether we should use pull-based model or push-based model. Intuitively, it must be clear that if we need to load some data on demand, piece by piece, then probably pull model is a way to go. And in contrast, if we are dealing with data representing some sorts of events that our application need to react to, then it makes sense to use push-based model. But let's just look at some code and start exploring the diversity of pull and push APIs. At the simplest level, we can express pull-based model as a function without parameters that returns some data of type T. But how many insights do we have by looking at this signature? Well, not much. Clearly, the signature doesn't tell us about all possible outcomes. So let's make it more precise by sprinkling it with effects. The first effect we're gonna cover is graceful termination. It means that we pulled all the available data and should stop calling the function. And we can express this effect by using the option of T return type, which models either having some value or absence of it. The next effect every C# programmer familiar with is exception. This effect means that some error occurred and we can get the results. C#, unlike Java, has no checked exceptions feature, and for great reasons, actually. But for our purpose, we would like to make this effect explicit. So we would convert control flow to data flow and use another wrapper type try, which expresses either having a value or exception. Now we made our signature super precise, but where can we get this function? As you may know, any problem in computer science can be solved with another level of indirection. That's a fundamental theorem of software engineering. One way of providing the indirection is using higher order function getPuller, which would return us the desired delegate instance. But we actually like object-oriented programming as C# programmers. So we put our pull method into iPuller interface and introduce one more interface with single getPuller function. Do this in
Andrew, I think your microphone cut out for a sec there.
Yeah, so yeah. Can you?
You're back.
So it's a well-known type, IEnumerable and IEnumerator, but try of option of T is decomposed here into method moveNext and property current. So what does this mean? It means that IEnumerable is the essence of pool-based data access API. Now we're gonna apply the trick that I learned from Eric Meyer and apply duality. In mathematics, duality translates concepts, theorems, and mathematical structures into other objects. By means of special involution operation. But when applied to function signatures, involution simply means swapping of inputs and outputs. So in our case, from super precise pool function signature, we get the push function taking a single parameter of type try of option of t and returning nothing. As previously, let's introduce another level of indirection and apply duality there. As a result, we get another two interfaces, iPushable and iPusher. And these interfaces should also look familiar. It is iObservable and iObserver from Reactive Extensions library. And just like in case of IEnumerator, try of option of t is decomposed, but now into three methods. So what we've got so far? So iObservable is the essence of push API and has deep mathematical relation to IEnumerable. They are dual, and it is possible to go from one interface to the other. But we forgot another important effect, latency, which tells us that function may take a long time to execute. There are two problems related to latency when working with interfaces that we've just discussed. The first one is problem of slow producer when calling the move next method on IEnumerator blocks the execution. And another slow consumer problem when the execution is blocked on next, on completer, and on error calls on iObserver. To solve these problems, we're gonna mix some asynchronicity into our interfaces. And in case of IEnumerable, apply an asynchronicity result in iAsync enumerable and iAsync enumerator, with the notable difference that move next now returns task of bool instead of just bool. And in second case, we get iAsync observable and iAsync observer with on next, on completed, and on error now being task returning. Let's put it all together. So I came up with the following graphical representation of types, the prism. So if we need to return one value synchronously, we just use the T return type. If we return many values in pool manner, we use IEnumerable, and in push manner, we use iObservable. But if we need to take latency into account, then we respectively use task of t, iAsync enumerable, and iAsync observable. Where are the async streams on this figure? Actually, there are three of them: iObservable, iAsync observable, and iAsync enumerable. They all employ asynchronicity, but slightly differ. We have diversity of types, each representing some combination of effects. And when designing our applications, we should choose accordingly to the desired effects instead of sticking to some particular type. What's interesting is that prism doesn't look like a complete puzzle, and we may consider extending it to the cube. What's on the other side of the cube? We're going to talk about in the end of the talk if we have enough time. Now, where to find these interfaces? Actually, They exist and for a long time already. So Async Enumerable was part of interactive extensions since 2009 or 10, and Async Observable is also part of Async RX and located in .NET Reactive repo. And there are a couple of F# implementations too. But what's important for our talk is that since .NET Standard 2.1, Async Enumerable and related types are now available in base class library, though there are some subtle differences from what we've seen so far. For instance, getAsync enumerator takes optional cancellation token parameter. Move next async returns value task of bool instead of task of bool. And in case your project targets .NET Standard 2.0 or compatible framework like .NET 4.6.1, you may use Microsoft BCL Async Interfaces NuGet package. It's nice to know that Async Enumerable is getting adoption. System Trading Channels library, which provides a set of data structures for asynchronous interaction between producers and consumers, exposes Async Enumerable from Channel Reader. Entity Framework Core allows to use asynchronous queries to avoid blocking thread while query is executed in the database. And a bunch of ASP.NET Core technologies are using Async enumerables for streaming capabilities. And we reached the part 2, C#8 to the rescue. Let's actually go to Visual Studio. So what we have here is a tiny Blazor WebAssembly application, which loads the list of issues for particular GitHub repo. So each issue has title, URL, author, a bunch of other properties too. And we have issues provider. So each issues provider performs GraphQL requests to GitHub, and each request returns some amount of issue objects, starting from some cursor, along with pagination information. And the first implementation, which we will consider, it uses a task of Async enumerable of issue return type. So what's going on here? So here we initialize a request, have a while loop, have some artificial delay for the sake of demo, and asynchronously get response. As we get the response, we append a chunk of issues to the resulting list here, report the progress to not stay completely silent. Then we check if we have any more data, or if we reached some limit to not exhaust the memory, and we break the loop. Otherwise, we proceed. Yeah, we update start cursor and continue the next iteration. Now let's take a look at the consumer side. So consumer side is a Razor page. Here's some markup as header, couple of buttons to start and stop loading. We display issues count and fill the table with issues data. What's interesting to look at is our start loading handler. So we reset issues, initialize some progress, which involves delegate each time the progress is reported. And then we create fresh cancellation token source, and actually asynchronously retrieve the data and notify about state changes. Let's actually try and run this code. Okay, the project is building. Okay. Yeah, so usually the first load takes longer time. Our application should be opened. Yeah, happy that we see that it loads. Okay, so let's click the load button, and we see that issues counter starts growing, and then we see the list of issues, and it's all clickable and working. Okay, but this approach has an obvious downside. We have to wait until all issues are loaded before we can show any of them. And because of that, we also have the artificial limit to not exhaust memory. So let's try to alleviate these problems and try another approach. This time we will try using IEnumerable of task of issue return type. Here we support the list of current page issues, and we keep track of the index inside of the current page. Then we have a infinite loop inside on each iteration we yield return the result of local function. Yes, and our local function is actually asynchronous, and it returns task of nullable issue. So at first here we check if we need to perform the new request. Yeah, if we didn't have any requests at all, or we exhausted the current page, so we asynchronously get the results, update the current page, and return item of current page and increment the index. But what's also important here, that if returned page is empty, we have no choice but to return the null value. So null value becomes the end marker of the sequence. Okay, now let's take a look at the consumer side. So what we have here is a for each loop, and each item represents the task. So we have to wait it, and in case it returns null, we break the loop. Otherwise, we add issue to the resultant list and update the page. So this approach has some improvements compared to previous one. So at least we can, show results as we download them. But it has downsides too. For instance, our producer function implicitly sets the requirements on consumer to await on each iteration. If we will ask for another item before awaiting the current one, we get invalid. We end up in invalid state. So this is not ideal. And let's try another approach actually. And another approach will use IObservable. So IObservable as we discussed earlier, yes, is a push-based model. So here we use this factory method, observable.create, which takes asynchronous lambda with two parameters, iObserver and cancellation token. And it's actually quite self-explaining. What we have here is a loop with asynchronous request, and as we iterate results of current response, we invoke this onNext method on iObserver. And if we reached the end of sequence, we just call onCompleted. So beautiful and precise. Let's open consumer code. And this code also looks very precise and clear. So we get the iObservable, we subscribe to results, and on each result we add issue to list of issues and update state. So this is a very cool approach. iObservable is a advanced technology, but we need to remember that this is a push-based API, and this means that we have to react at the speed of producer. Otherwise, we will get stuck, and iObservable will not be as useful as it could be. Some implementations like reactive streams actually have a side channel to communicate the back pressure, or in other words, tell the producer to slow down. And all the discussed approaches, they were available before C#8, and well, they are still available, but C#8 allows us to use another approach. So this is another implementation that makes use of async iterators. So C#8 allows to combine, to use both await and yield returns inside one method, and such method is called async iterator. Async iterators, they have this async modifier, and they have either async enumerable or async iterator return type. I think this code is also very simple. We just await where we want to await, and we yield return where we want to yield return. Now consumer code. So here we use another feature of C#8, which allows us to consume async streams using asynchronous for each, which writes like regular for each, but there is a await keyword at the start of this statement. So it looks just like synchronous for each, but all the asynchronicity is hidden behind this little keyword, which is, super cool. Let's actually run the example and take a look that it actually works. So okay, application is loading. Select this implementation. Yeah, and we get the results as soon as we retrieve them. Awesome. So to conclude, C#8 provides language support to easily and efficiently produce and consume async enumerables. But C# is not a pioneer here. Dart, Python, JavaScript, F#, C++, and Kotlin, all these languages have similar feature and for a while already. So C# is keeping up, sort of. And we reached the third part, lowering, the art of deception. So almost 20 years ago, famous Kevin Mitnick wrote the book, The Art of Deception, that covered social engineering. But today we're gonna talk about compiler engineering. So lowering is a technique actively used by C# compiler, well, other compilers too, which consists of rewriting high-level C# features into low-level C# features. Apparently, both async iterators and await for each that we talked about previously are in some sense a big piece of deception because compiler completely rewrites them. And I think it's quite interesting to take a look at what's going on behind the scenes. Let's actually start with a regular for each statement. So probably many of you know that compiler rewrites it into code like this. So we get an enumerator, inside try block we loop while move next returns true, and access current item through current property. And in final block we call dispose on enumerator. Pretty straightforward. Now let's take a look at asynchronous for each. And actually it's lowered just like regular for each, but methods and here have async somewhere in their name, and there are awaits of move next async and dispose async. And just like regular for each, asynchronous for each can work with any collection type as long as it has suitable shape. What are the shape requirements here? Well, collection type should have getAsync enumerator method, which actually may have a single optional or params parameter. Move next async should return awaitable type, and awaitability is also a type pattern. So you can see that type patterns are used in C# all over the place. And dispose async method is completely optional. No method, no call. But if there is a method, then return type should be awaitable as well. Now let's consider the following example. We have a struct implementing async enumerable of int interface. C# allows to omit default value of parameters when implementing interface members. And we have this little print method, which iterates over this. What's going on here? So compiler checks whether getAsync enumerator method is suitable. Does it have single optional or params parameter? Well, no, it has required single parameter, not optional. So it means that we need to convert this into async enumerable interface instance, which means that we have boxing. How to avoid boxing? Just add default parameter value, and that's it. And this example actually shows how understanding of lowering can save you from unwanted performance penalties. Now, let's switch to another demo. Okay. So, yeah, async enumerable has a couple of useful extension methods defined on it, with cancellation and configure await, and both of them return the same type. Let's take a look at the definition. So yes, and we see that configured cancelable async enumerable doesn't implement async enumerable interface. However, it has suitable shape, and therefore it can be enumerated with await for each. Here we see that it has get async enumerator, which calls get async enumerator on original enumerable, but passes cancellation token there. And we have this return type enumerator, which is also read-only struct, and it has all this move next async, current, and dispose async. So even framework makes use of this type pattern. In our example, we explicitly pass cancellation token into async iterator. However, in some cases, all what we have on input is async enumerable, and we have no knowledge if it's cancelable in any way. So in such cases, with cancellation is extremely useful. But let's actually provide a second cancellation token and see if it works. So I will duplicate cancellation token source here. I will also copy paste this code, and let's update it here, and we name it CT2, so cancellation token 2, pass it here. Then we will copy this handler as well, name it cancel loading 2. Yeah, and we actually need one more button here, which we will trigger this handler. Okay, let's run the code. Yeah, so our project is building. Okay, it's loading. Yes, click load. Yeah, click cancel 2, and it doesn't work. What the actual heck? Cancel works. Okay, let's take a look. What's the problem here? So if we will go to definition of our async iterator method, we can see that cancellation token is marked with compiler warning. Async iterator has one or more parameters of type cancellation token, but none of them is decorated with enumerator cancellation attribute. So the cancellation token parameter from the generated blah 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 will be unconsumed. So here is a solution to our problem. I think we will not run the sample again, just for saving some time, but believe me, it works now. Okay, now let's discuss lowering of async iterators. Just like in case of regular iterators and async methods, C# compiler generates the beautiful thing called state machine. As practically all compiler generated entities, it has unpronounceable name, which is why I called it here Voldemort state machine. So what is a state machine actually? So state machine is a model of computation described by the set of states and transitions between states. And let's take a look at the states and transitions of async iterator. So state machine is created in finished state, and get async enumerator moves it into initial state. When consumer asks for first element, we move to running state. And at this point, we actually start executing the code. At some point, we may hit a wait of async operation, which suspends the execution and move us to suspended state. Later, this async operation resumes, and state machine re-enters the running state. When we hit yield return, we finally reach the yield state, and we stay in this state until consumer asks for the next element. Then state machine is spinning around this running suspended yield states, but finally it reaches the finished state either by completing normally or with exception. Now let's take a look at the class generated class again. So it implements a bunch of interfaces. Of course, it implements async enumerable as that's what we have as our return type, but it also implements async enumerator. It allows us not only not to generate the second class, but also it allows us to return this from getAsync enumerator, but only if getAsync enumerator is called on the same thread that state machine was created. Also, we have a couple of these interesting interfaces: I-value task source of bool and I-value task source, non-generic one. Why do we need these? So, as we showed earlier, state machine implements async enumerator interface and must provide two async methods: move next async and dispose async, which return value task of bool and non-generic value task. Using value tasks as return type allows to avoid task of T object allocation if method completes synchronously, but can we reduce allocations on asynchronous completion path as well? It turns out if usage pattern doesn't allow to run multiple asynchronous operations concurrently, then we can reuse single object representing completion of async operation. And that's exactly the case with async iterators. So we request items one by one. We never run multiple move next async operations concurrently. Instead, we invoke move next async, wait for its completion, and only then request the next item. To support this pattern, value task has got a constructor taking I-value task source. And implementation of move next async and dispose async can pass this reference there. You can imagine that implementation of I-value task source interface can be non-trivial, and it is. However, base class library provides the standard implementation as a manual reset value task source core type, and generated state machine just delegates everything into a field of this type. Now let's take a look at the decompiled code. I think I need to tweak one option. Yes, I need to uncheck use sources from symbols. So we didn't, so we actually could decompile and not use our program sources. So here we have our issues provider. Let's open our implementation. So we see that this method is marked with async iterator state machine attribute. And as we remember, it has cancellation token parameter. Here we create state machine object, and we store parameters, including cancellation token, into its field and return it. So let's take a look at the generated state machine. So as we discussed, it is a compiler generated class implementing a bunch of interfaces. It has this manual reset value task source core field, along with lots of other fields. And it has this giant method move next, the core logic of state machine, with lots of go-to statements. So arguably, go-to statement is considered useful if it's generated. But what is interesting is a get async enumerator method. Yeah, I actually forgot to compile the code after I added enumerator cancellation attribute. Oh, let's do this. Okay. Let's update the code. And scroll down to get async enumerator. So remember that we have cancellation token original one stored in the field. And we also have additional cancellation token coming to get async enumerator. And this code actually, so what it does, it checks if both cancellation tokens are not equal and have non-default value, then we combine them with cancellation token source, create linked token source method. So that's how it actually works. If you want to actually see how lowering of async iterators is implemented in the compiler, I invite you to download the Roslyn source codes or visit sourceroslyn.io and look at the async iterator rewriter class. It's quite readable and has lots of comments. And we reached the final part, the art of async querying. We all love LINQ, and ReSharper is known for its ability to rewrite these nasty imperative for each loops into beautiful sequences of standard LINQ operators, making the code declarative and super clear. But the LINQ we all know is defined on IEnumerable and can be used with IAsync enumerables. And although .NET Standard 2.1 includes IAsync enumerable, unfortunately it doesn't provide all those extension methods that are required for LINQ to work. So do we need to sit down and implement them ourselves? Fortunately, no. There is an existing NuGet package, system LINQ async. With all extension methods in place, we can easily use query comprehension syntax, which is another C# feature based on type pattern actually. But what we still can do is we can't use a weight expression in there. But who knows, maybe we will get it in 5 years or so. let's get back to our demo. So let me uncomment this line to include this package reference. Okay, what I'm gonna do is I will try writing some request, some query actually, yes. So let's try to get nullable reference types issues. What we're gonna do, we will we'll invoke our method, pass owner name, repo name there, and yeah, we actually need to invoke double completion here, so that postfix for each postfix template item is available here, and when we complete it, async modifier is added. Now let's check if issue categorize equals to nullable reference types, and if this is the case, we will return issue. And now we need to fix the return type. Yeah, okay. So you can notice that there is a little squiggle thing there. It says loop can be converted into a LINQ expression. So let's try. Oh my, so yeah, we're using asynchronous LINQ there. Now let's try to convert LINQ to code again. Yeah, and it works too. Yeah, so I actually implemented this feature around 1 week ago. So it will be available in the upcoming version of ReSharper and Writer. But now I would like to do something else. Let's extract this expression into separate method and call it predicate. And what we're gonna do is we will use some asynchronous operation here, like task delay. Let's fix the return type here, and let's await this call. And you know, we still have this squiggle. So let's try. Oh, that's something new. So we have not just simple where, we have where await. Yeah, and this where await method, it actually takes a predicate that returns task. Yeah, so async LINQ is not just like ordinary regular LINQ. It has some additional operations which take asynchronicity into account. Actually, there is one more family of functions that end with await with cancellation suffix. Yeah, and we can pass. Yeah, there is an additional parameter here, cancellation token. Yeah, all right. Okay. But as we talk about querying, what about iQueryable? So iQueryable is super cool because it allows to offload some computations somewhere remotely. And it is allowed because in C# Lambda expressions are convertible not only to delegate types, but also to expression trees. Let's take a look at the prism we have seen before and think, what's the place for iQueryable here? I actually thought about this and came up with another dimension. So I call this dimension code as data. It's quite obvious that iQueryable corresponds to IEnumerable, but if there is a correspondence for this one, there should be something for other types as well. Well, let's actually fill the gaps, and we will have the following types. So for singular result, we will have iQueryable scalar type. For observable, we'll have iQueryable observable or simply observable, and there are types that take asynchronicity latency into account. And apparently, some of these types do exist as part of .NET Reactive repo. So reactive extensions, RX Rocks, and other two types, queryable scalar and async queryable scalar, we can actually implement them using the take one operation. So summary, there is a diversity of async streams. .NET Standard 2.1 introduced standard API for pool-based async streams. C# is keeping up with other modern languages, and ReSharper and Rider are always here to support you. I think we're reaching time limit, and I should stop here. Okay.
All right, great session, Andrew. Thank you. I have a couple of questions from the audience, and let's maybe start with the one that was asked most in the past couple of minutes or the past hour. And that is, can people find your samples somewhere online?
Yeah, so I will post them. So currently they are in private GitHub repo, and I will make it public.
All right, cool. So they just search your name on GitHub, I guess.
Yeah, I actually had it somewhere in the beginning. Whoa. Yeah, so I go with a Karpov 89 handle everywhere.
All right, perfect. Then let's go for the heavier questions. One is, what are your recommendations regarding converting a push-based stream into pull-based? Are channels the most efficient way to do that, or?
So, yeah, probably channels are efficient way, but you should know what you are doing, because you should select one of these collections based on your requirements. If you do need to convert push API into pull, there certainly can be some work to do, because pulling can be slower than pushing, and you need to put some buffers in place, and you can create channels with such buffers. Yeah.
Right, cool. Follow-up question on that one is, how would you go about merging two pull-based streams? So for example, if you have two stream readers and you want to read them line by line from both simultaneously, how would you yield the lines that come in from those two?
Okay, yeah, great question. Well, actually, you can take a look at the zip operation that is defined in async system link async, and take a look at its implementation. So zip operation takes two async enumerables and produces the result.
All right, cool. Yeah, there's another question on what are the best use cases to use all of these interfaces. When should you avoid using them?
So I showed you the diversity of types and recommendation. Look at your requirements. Look if you need to take latency into account, and take a look at the kind of data you are working with. If it's inherently pool-based data source, use pool, and if it represents some sort of stream of events, then use push. And yeah, I had this prism. Yeah, so you can select the collection type based on pool push and latency axes.
All right, cool. Then maybe one more to end the session with, and that is how do you catch exceptions in the iterator? So for example, the place where you do the yield return, can you just put a try catch around that, or is there a better way?
Yeah, so async iterators work just like regular iterators in this sense. So if you get an exception, you can easily catch it with try catch block. You don't need to advise some new smart mechanisms about it. Yeah, you're just catching an exception, and that's what I have here in my code. So I have this wait for each loop, and it is in try catch block where I catch iteration cancelled exception. Yeah, simple as.
I think the question was more about your get issue async method there. If in that one there's an exception, how do you catch the exception internally in that method?
Yeah, so just use try catch, yeah, and it works.
So it should work around line 167, right?
Yeah, sure.
All right, perfect. Thanks. A couple of other questions coming in. Let's maybe end with one, and also one compliment, which is that the prism that you drew on slides is amazing, and people are probably going to reuse that one. One question that is left, and that is why should you prefer the async enumerables over RX framework?
Well, you shouldn't just blindly prefer it. You just weigh your requirements. That's what I say everywhere. People ask me about that. So if you are working with a pool-based API, use async enumerable. If you work with a stream of events, use iObservable.
All right, cool. That makes sense. There's a couple of other questions that we'll handle via text. But other than that, I guess we can wrap up here. Thank you again for a very interesting session. Thanks everyone for joining us.